Yeah, so welcome everybody to today's STEMS webinar. So we are very happy to have Jonathan Lilly as our speaker today. So Jonathan is currently a senior scientist at the Planetary Science Institute in Arizona. He also holds a visiting scientist appointment at the University of Toronto at the Department of Physics, as well as he's working with this company Ocean Box in Norway as a lead oceanographer. So he's a physical oceanographer by training and very well known for his work in that area. So his PhD is in physical oceanography from the University of Washington. After his PhD, he spent some time in France as a postdoc at an oceanography lab. After which he has been a senior scientist, as a research scientist or a senior research scientist at various research institutes, which include the Earth and Space Research, Northwest Research Associates, and TICE Research. And currently he's with the Planetary Science Institute. So he has various research interests in physical oceanography. What is particularly relevant for us is that he's interested in statistical methods for ocean data analysis, and we will be hearing about that in the talk. But he also has interest in things like vortex structures, Lagrangian observations, and high latitude oceanography. But today we will be hearing about his work on mapping of oceanographic data. So unless it has changed, his title is Local Polynomial Fitting on the Sphere, a Mapping Solution for the Earth Sciences. So Jonathan, please take it away.
Excellent. Thanks so much, Mikhail. And thanks very much for inviting me to give this talk. I'm really happy to talk to this audience, and I'm also really happy to present this material. This is material that I have been working on for a ridiculously long time, and it's one of those things that sometimes you think, why didn't I publish that years ago? Anyway, it's like that. So this talk has given me the opportunity to um, revisit that material, remember what I've been doing, and hopefully try to get it out and be published in the next little while. So this is my website. I just want to go here because I can show you that if you go to talks, here we are um, at this top one here, and that's it's already online, so you can just you know get it there later if you'd like. Okay, local polynomial fitting on the sphere, a mapping solution for other sciences. Let's Okay. So I'm an oceanographer. I work with different oceanographic data sets. This is one of my absolute favorite data sets. There's a series of satellites that observe the ocean surface. They're called altimeters. They look down from, space, and they can detect the height of the surface of the ocean to within like at least a centimeter, maybe a couple millimeters. And they observe the ocean surface along these tracks, which I've drawn here. Can you guys see my mouse if I go like that? Yeah. Okay.
Yes,
So
yes, yes, I can see. Yes.
they observe it along all these tracks. Okay. So these are called altimeter tracks. By the way, do feel free if anybody has questions, feel free to jump in at any time. There's no need to wait till the end. Because also it's a diverse audience. I don't know what you guys know. Um, so feel free. Anyway, so we have these long track altimeters. And the oldest kind of classic one dates back until 1992. So it's just one of the most amazing data sets you could ask for. There's a big step though, which is that what we want is a map of the sea surface height as a function of latitude and longitude. And what we have is the sea surface height along these tracks. So this turns in sometime, which sometimes there's data gaps and stuff like this. So this becomes a mapping problem, a problem mapping scattered data, which is a central statistical problem that comes up in many different fields. So that's what I'm going to be talking about today. Um, so there currently is a mapped product for this long track data. It's known as CMEMS. If you're an oceanographer, that means something to you. But it's really a very heavily used product, but it can definitely be improved for a few reasons. First of all, it's not open source. The algorithm is quite complex. We don't know exactly what it's doing. They won't tell us exactly what the parameters are. So it's a big black box, and we don't know exactly what's happening. And this has led to a number of problems where you see something that seems like an artifact or maybe it's real, and you can't actually check the source to know what it is. So it's a real big headache for you know certain kinds of studies to not know the actual algorithm. In addition, as I'll show you, it's probably quite oversmoothed. So I'm sure we can do a better job. So I'm going to present an alternative today using a very simple algorithm. To keep things simple, I'm going to use only a subset of all the available along track altimeters that there are. So this one I showed you here, this is the track pattern for a certain altimeter known as the Jason class. This goes back to 92. But there's also like dozens of other altimeter missions with different track patterns available for certain different times. So it's a very heterogeneous and slightly um, messy data set if you consider everything. So for simplicity, I'm going to just consider the JSON class data. This means we're already at a disadvantage by not using as much data as is available, but it lets us test the algorithm and it keeps things simple. All right. So at the top um, is a map of the sea surface height anomaly produced by CMEMS. So this is the standard map product. What we're looking at here is places where there's a bump in the ocean or a depression in the ocean surface. And these bumps and depressions are very important because they're actually telling us about the currents. So if you stir your coffee with a spoon and it makes a little swirl, that swirl has a little surface depression, which I'm sure you've seen. And if you multiply that by 10 million or 100 million, you get vortices that are the size of, a city. And that's what we're seeing here, among other things. We're seeing dynamical features that imprint themselves upon the sea surface height. Also, because of some particular dynamics on a rotating sphere, you can actually infer the leading order currents by knowing the gradients in the sea surface height. Anyway, so the top field is showing us the anomalies, that is the deviations from a long-term mean. And you see a lot of eddy activity, these uh, kind of areas where there's lots of red and blue. That's like the Gulf Stream. Down here we have another major current called the Agulhas current. And then you see a lot of stuff tends to propagate westward. Anyway, there's a whole bunch of features that we're not going to necessarily need to get into. The point is, if you look down at this lower panel down here, this is a method I produced. This is a product I produced with the method I'm going to show you today. And if you compare these two maps, the upper one is like a major national effort made by France. The lower one is one I made in my garage, and they're almost identical. And this shows, even though I'm using only a fraction of the data. So this is a proof of concept, and it indicates that if we use all the data, we're definitely going to make a superior product, and it's going to be open source. So I hope to get to that over the next few years. Okay, I think I said all this already, so I'll skip it. Okay, so let's talk about mapping scattered data. This is a major problem in statistical analysis, and as such, there's a number of different methods. Now, some of you, like for example, Mikhail may know a lot more about this than me. But one thing that's really interesting is you've got these different methods, and they keep getting rediscovered in different fields with different names. Now, if you're trying to dive into a field and see like what method should I use, it's super annoying because each of these, like for example, optimal interpolation, as it's called in the oceanographic community, is also known as Gauss-Markov interpolation, is also known as simple Kriging in geophysics. Local polynomial fitting which I'm talking about today, is also known as locally weighted least squares regression. LOES, for some bizarre reason, in oceanography, it's called LOES in the geosciences, which is an analogy to like windblown sediments. Um, and each of these fields has their own literature and their own terminology and their own decisions that they've made over the years. So it's a lot. And it's a problem, in my opinion, of if you want to know the best answer, you really have to surmount these this disparity and try to unify it in some way. Anyway, so the four main methods, we have optimal interpolation, smoothing splines, local polynomial fitting, which I'll talk about today, And kernel smoothing, which is very simple, it just means you smooth it with the convolution. That's actually a subset of local polynomial fitting. So uh, all these methods that I just described are linear in the data. And this means that in a certain sense, they're all equivalent. In other words, if you're working with a smoothing spline and you tell me the norm that you used, there's some way that I should be able to tell you a kernel and an order to apply in a local polynomial fitting that gives you the same answer. And so there's some kind of exact equivalence that you can connect the arrows between all these things. And there's been some really interesting work done in that direction, but completing all of those arrows is incomplete as far as I know. So I just want to point that out as a really interesting topic for future work, but we're not going to have time to get any more into that today. I'm looking at local polynomial fitting for a few reasons. It's very simple, it's fast, it's easy to implement and easy to adjust. It has very good performance with irregular data spacing. It doesn't require you to make any assumptions about your data, or for example, to specify a covariance function. There's a huge body of theoretical results, and also you get estimates of the surface derivatives for free as a part of this process. Um, what it hasn't yet been generalized to the sphere, as far as I know. I'm going to show a very simple generalization that's quite easy to do. All right. So local polynomial fitting, as the name implies, you've got some point that you're interested in taking your scattered data and using it to find the value at a certain point. We're going to call that point x naught, y naught. And of course, we're going to then vary this point so it becomes every point on a grid, but it suffices to consider one point. So we're going to be looking at the weighted square error between the observations um, and a pth order polynomial fit. Um, you arrange the observations into vectors of x and y locations. So this is, I'm showing you a particular form of this problem that is appropriate for 2 dimensions. So what you end up with is the mean squared error is the observations minus this thing here is, as I'll show you, is like a polynomial, and this thing here is your solution, and this is a weight. So what this is saying is that basically the weighted difference between the fit and the observations is defined as this delta squared, and we're trying to make this as small as possible. There's only really 3 parameters that control this. There's the order of the fit, which I'll tell you more about on the next page. And then there's 2 properties of this weight. There's the nature, the shape of the weighting function, and then there's like a radius, which is known as the bandwidth. Um, so the this estimate vector here, which is called beta hat, that is going to vary depending on whether you've got a zeroth, first, or second order fit. Zeroth order fit means you're fitting to a constant locally. A first order fit means you're fitting to a plane. And a second order fit means you're fitting to a parabolic surface or second order surface. So what this means is that like if you're doing a first order fit, you're fitting not only to the value of the surface, but also to its derivatives at that point. And similarly for a second order fit, you're fitting in addition the 3 curvature terms. Um, so this is the vector that you're fitting to as a function of the order p. And then this is what that this kind of matrix of polynomials looks like. It's just a thing that you need to multiply by the solution vector in order to have a local Taylor series expansion. So all you're doing here is you're doing a local Taylor series expansion and trying to find the best choice of coefficients for a given order. Any questions about that? Has this like, is everybody like, yeah, yeah, we know? Is this super familiar to people? Okay, no reaction, so I'm guessing it's not super familiar, but also not super confusing. Okay, that's good. Now we get to this weighting matrix. The weighting matrix is a diagonal matrix, and it's normally composed of this, or not, doesn't have to be diagonal matrix, but the easiest one that we'll work with today is diagonal. So you just have some function k, which is called the kernel, and it's normally a symmetric decaying function of distance. And then, so what you can choose is what does this k look like? And the other thing you can choose is this value of h here, which is called the bandwidth. And that sets basically how far away do you want to grab um, data points from. Um, so this has a very well-known solution. You can just write it down as a matrix inversion and then times some other stuff. So solving this problem to minimize the least squares error once you've specified um, uh, all of your parameters is really a snap. And notably, the matrix here that you're inverting is a small matrix. This direction here is what I'm calling Q. So it's 1, 3, or 6. And so you're inverting like a uh like a 3 by 3 or 6 by 6 matrix. So it's not a very difficult problem. It is possible, and this is something I'm thinking about for the future, to make this a anisotropic um, weight, so that basically you have like instead of circular contours of constant weight, there are elliptical contours of constant weight. That's pretty promising, but we're not going to talk about it today. But it can be done, and there's a little bit. There's only a few places I've seen this worked out. One of which is the very nice book by Fanning Geibels on local polynomial fitting. They have some work on elliptical fits. Okay, so let's take a look at how this is working in practice. You guys see the little orange dots over here? Okay,
It's pretty small, I must say.
let me see. How about
You can
this?
zoom. Yeah, that helps a
Whoops.
lot.
Whoa,
Yeah,
that was
that
terrible. Let
helps.
me try again. See if I can do that. Okay. Oh, damn. Okay, so the trick is that I have to zoom, but I can't go up or down. So I'll try one more time. Okay. So you see the little orange dots. And the way I've arranged these little orange dots is that there's more higher density of the orange dots towards the top and a lower density down here. Okay. So this is my true surface. And then if I choose and then then the shading here is the field that I'm observing. So let's just call it C surface height, okay? Now, if you do a zeroth order fit, a zeroth order fit is the exact same thing as I just take some convolution function and I convolve it, okay? Or it's the same thing as at every point that I want the map at, I fit locally in some radius to a constant. Those are the same problem. And what you get is absolutely terrible. You get these kind of thumbprint looking things, and you see your contours of the constant value of your field are all distorted. Okay, so what's going on here? Well, it's really interesting actually. If you turn to a first order fit, that completely goes away. Okay, so there's no longer these terrible um, um, deformations and these bumps, these thumbprints. These thumbprints are like the imprint of the data. Okay, so here now in this case, you see guys see this little circle here? That's the radius that I'm fitting in. So I'm choosing everything in this radius. And as you can see, sometimes there's just not enough. So I don't know what to do. And that's what's happening over here. A first order fit is doing great when there's enough data. But because I'm using a fixed radius, if there's not enough data nearby, I don't know what to do. So I get these white patches of nothing. Okay. So, so then this first order fit removes this bias problem. But then what you can do is you can do a thing called it's called a variable bandwidth, which means that the radius of the fit can expand. And rather than the word variable bandwidth, I like to talk about a constant population. So now what we're going to do is rather than having our circle be a constant radius, the circle is going to grow to encompass a fixed number of points. And when we do that, now I'm showing you very faintly here. Let's see if I can zoom in and not mess anything up. Very faintly, you can see there's all different sized circles over here now on the right. And when you combine the first order fit with with uh, the fixed population choice of bandwidth, that is the bandwidth you're looking over for your data is expanding to get the same number of points, then you get back basically exactly what you put in. Okay, so what's happening here? So it turns out that the zeroth order fit has a severe defect. And this defect is when both the density of observations, that's the red points are have a gradient. The density of observations has a gradient, and the field has a gradient. And here I have a gradient because I'm going from dark blue to light blue. When you have gradients in both things, you get a huge bias term. And that's a really big problem. And that is why you should not use this. You should not use this unless the field you're estimating is constant, which is so boring you would never do it. This was now the first order fit doesn't have that. That bias term drops away. And Fan in 1992 paper explained this really well. And he calls the high order fits. He says that they're design adaptive, and the design is what the design means in this context. Design means the distribution of sampling points. So design adaptive means that the method adapts to the distribution of sampling points and uh, and doesn't lead to this bias. So the takeaway from this, and this is not my work, this is just kind of out there in the literature, is that the combination of a higher than zeroth order fit with a variable bandwidth works great. And it naturally adapts to what you do, and it gives you really to what you have, and it gives you nice looking maps with very little effort. So now we're going to go on and I'm going to show you some.
John, can I take you up on your offer to ask
Yeah,
questions
sure
along the
thing,
way
sure
for this
thing. Yeah,
geometry?
yeah.
It's not obvious to me in the last plot on the far right that, okay, so you have no more gaps because of the
Oh,
variable
sorry.
width.
Sorry about that. Yeah. Yeah.
Let me zoom in. But certainly your estimate is still not perfect, right? There's going to be some error. Maybe, oh, maybe there are gaps. It's a little hard to see. They come and go in the rendering. Are there still gaps or no?
It's
It's filled
there's
in, but there still has to be an error relative to your true.
the error is essentially minuscule, and the reason it's minuscule is that this problem I've set up the field I'm mapping is a linear gradient.
Right.
And the linear fit does a fantastic job at mapping a linear gradient. Also, this data has no noise in it. So
Yeah.
I
Right.
think that if you looked at the residual, it'd be like numerical noise in this particular case of a noise-free data set and
Yeah.
only a linear gradient.
Okay.
Yeah. So okay. Great. Any other questions? Okay. Somehow I did something. Now I don't see you guys anymore. Whatever. Just I can't see if you raise your hand, so just talk. Okay, so now I'm going to show you some of my work. All right. This kernel function or weighting function. This is something that I mean you often find like people just make propositions. Let's try this form. Let's try this form. And there's actually a lot of different forms that have been proposed out there. But if you want to make a comparison between them, you need something that unifies that. So I propose this very simple generalized kind of kernel shape. The if you cover up this beta here, cross out this beta and make this alpha a 2, that's kind of a classic weighting kernel called the Epenichnikov kernel that has some nice asymptotic properties. Whether they work out in reality is not clear. So this is essentially a generalization that this, by the way, you have some weight that is going to decay to a certain radius, and then you set it to 0. So essentially, you have these two parameters are controlling the way that this radius is decaying, and then outside of some distance, which we just choose as 1, you set the whole thing to 0. So I'll show you this in a second. So having a unified form is really nice because when we do our numerical experiments in a little bit, we can we can do um, basically parameter sweeps to try to see what is the best choice of these parameters. There's also a very nice reparameterization of this where you could think about it instead of these two parameters. You could think about it as a shape and a half power radius. So let me show you what that looks like. Um, so if you choose alpha equals 2 and so in these curves, I'm varying beta here, and the kernel is defined outside of radius 1 to equal 0. But if I show you this in a different way and I stack all these curves so that they have that their half power point is at the same place, I just rescale the x-axis, then it looks like this. This shows you their shape better. So essentially, you have something that's transitioning from a Gaussian-ish kind of thing, but one that has a definite end to a top hat or step function. So that's a very nice kind of a family of transitions. And as you change this alpha parameter, then you kind of can squeeze the weighting function further out and further in like this. So anyway, this is a nice parameter, nice family of forms that lets us do some playing around. Okay. All I want to say about this is that there's theory out there that lets you, if you don't know the correct answer, it lets you estimate the correct answer from your actual observations. And actually, it doesn't do a bad job. So that's another thing I like about this method is that there's theory out there such that you can estimate your bias and you can estimate your variance. That's all I want to say about that at the moment. Okay. For the generalization to the sphere, well, it's actually pretty straightforward. All we're going to do is we're going to, if we're interested in a map at this point where the black dot is, we just project everything into the tangent plane. And after we project it into the tangent plane, then we can just do the local polynomial fitting in X and Y as we did previously. And this is very simple, but it works great. And um, you don't have to worry about the fact that the latitude and longitude coordinates are changing around and as you move. You're always dealing with locally X, Y coordinates. Um, Here is how that looks algebraically, but I don't think it's that illuminating, so I'll just continue. But you have it here if you want to see it later. Okay. So here's how we're going to determine the best choice of parameters that we can apply to our data. We're going to use a model, and I don't know if you guys use this term, but in oceanography, people call it an observing system simulation experiment. We take a model of the ocean, we sample it exactly like we would sample exactly like the altimeter sampling the actual ocean. And then because we know the true answer, we know the right answer, we can compare our maps of sea surface height to the truth, and then we can minimize whatever we like. In this case, I'm going to minimize the just the globally integrated mean square error. So that's what we're going to do. We're going to do a giant parameter sweep through um, uh, through the main parameters controlling the local polynomial fit to find out what is going to do the best job in this model, and then we're going to apply that to the data. And we're going to let the parameters have a latitude dependence. So, and then what we find is that the linear and quadratic fits, as you would expect, are much better than the zeroth order fit. So we're not even going to look at the zeroth order fit, but I'm going to show you the quadratic fit. Okay. So we do I don't remember exactly how many, but it was something like 10,000 different fits, which I then distill, and this is showing you the sensitivity to three parameters around the optimal values. So the gray lines are fits to the optimal choice of these parameters, and then we're we're varying, like I'm varying this one while holding these other two constant, and then I'm varying this one while holding these other two constant, and so forth. And then what we're seeing here as a function of latitude, the color is the longitudinally integrated error. So what this panel is saying is, and the dots are at each latitude band, and then the line is a parametric fit. I just chose it. Whoops, chose a parametric model to kind of capture this shape. So these high values here are large error, and the low values are low error. The bright values are low error. So what this is saying is that the best choice of the inner radius, that's the half power radius, is one that is going to increase as you go towards the equator. And it's this what's happening down here is that when you get too small, you end up with like places where the inversion fails. It's like you get a condition number problem basically. And so when you make it too small, then you just get terrible results. So that's what's happening down here is where there's you're just it's just too small for good answers everywhere. But if you're just slightly larger than that, then it works. Then that's where your minimum is. And so there's a strong dependence on this inner radius. Then the population, which is the number of data points that we're encompassing, actually, the fact that you don't see any changes from left to right here means the population is actually not a very strong controller of the fit quality, and neither is the shape parameter. So the shape parameter, the minimum's kind of around 2, which is the Gaussian-like family, but it doesn't have these strong gradients as does the inner radius. And this is a little bit this doesn't really match the asymptotic theory. The asymptotic theory says that the this Epineshnikov kernel should be ideal, and it also says, or the conventional wisdom anyway, is that the specific shape of the kernel shouldn't matter that much anyway. And that's not what we find here. We find that the um, the the choice of kernel does matter, and the parameter that matters is the inner radius. That's really the most important one for this particular problem. It might be different for other problems. Um, so I'm converting these parameters to slightly different forms. I have now this is the black is the inner radius, optimal inner radius choice, and the gray represents some places where it's just not possible to meet that for the reasons of the topographic constraints. This one is that you convert the population into an outer radius, and because the population is fixed spatially, but the data density is not, that means that actually this outer radius or bandwidth is going to change spatially, as will, and I've converted here into this beta parameter. But let me show you what this one looks like spatially. So that is basically just a big stripe where you are wanting to use this larger radius where you're at the equator. And then the optimal bandwidth is, again, we're keeping the population fixed. So the population is 500. But that means the optimal bandwidth is growing and shrinking because because of this grid pattern, you're trying to encompass the same amount of data points. Especially around the coast, you see that you need to make the bandwidth bigger because you only have half the data points available to you. So conventional wisdom says that you want to smooth using spatially fixed parameters in order to avoid artifacts, but that's really not true when you're working with higher order fits because they're design adaptive. And actually, the fact that you're letting the parameters vary spatially is helping you to account for the inhomogeneity of this sampling pattern. So, okay, so now let's talk about the error. This is the error using the best parameters that I could come up with, um, which are these. Um, then I look at the mean error in the model between truth and um, and my fit, and you see that perhaps expectedly, you have errors that present the imprint of the sampling pattern, not surprisingly. So and you see there's large error here, large errors kind of down here. These are over the major ocean currents. So what's going on here? Well, what is the physical property of the field that is inducing these errors? Um, this is the Laplacian magnitude, so it's the essentially measure of curvature. What this is saying is that when the surface is curved, that's where we're seeing this error. So the surface is curved here, 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 and those are all the places we're seeing a lot of error. Okay, so what's going on here? Let's zoom in on this region over here, which is the Gulf Stream region. Okay, so this is um, the true field, the snapshot of the true field in the Gulf Stream region with the sampling pattern shown. And these kind of pluses and minuses, these are these like basically eddy features um, associated with the Gulf Stream. When you subtract the true field, and then you take the true field, you subtract the fit, you get this, okay? So what do you notice? You notice that pluses and minuses fall in between the grid locations. So now we understand where this error is coming from. It's coming from the fact that the features that we're trying to map have curvature on the scale of the grid on which we're sampling. And sometimes the interesting features just fall smack in between our observations and we don't see them at all. Now, that means that within the context of this local polynomial fitting that we're talking about now, it's really unlikely that you could improve on this because you just don't know anything about this point. There are other methods that some colleagues are working on that can basically um, uh, account for the fact that these features are moving to try to fill in that information. But as far as the local polynomial fitting, I think you probably won't improve on what we've got. You're just kind of stuck with this curvature error. Okay, so let me just, we're getting to the wrap-up phase. So let me just tell you a bit about I don't know if in your guys' fields what people like to do for mapping, but in oceanography, um, optimal interpolation is by far the most common mapping method. In fact, people don't like by orders of magnitude, it's more common, and people aren't really very familiar with local polynomial fitting. So here are some of the reasons why I favor the local polynomial fitting in this context. It doesn't require a prior knowledge of the covariance structure of the field that you're mapping. You can choose the optimal parameters either empirically, as we're doing with this kind of experiment, or using, there's also a theory to try to estimate the optimal parameters. You have several degrees of adjustability, whereas strictly speaking, optimal interpolation doesn't have any because you're supposed to use the true covariance function. It's actually, I don't know if everybody appreciates this, but local polynomial fitting is much faster because the matrix you're inverting is much smaller. You're inverting something like a 3 by 3 or 6 by 6 matrix as opposed to a matrix that's the size of your observations, which could be 200 by 200 or something like this. Also, although optimal interpolation is theoretically optimal in some sense, the real world behavior doesn't necessarily reflect that. And the sense of optimality is crucial. So in oceanography, like people are trying to study these bumps or eddies, but the purpose of optimal interpolation is to smooth over them to get a good estimate of the mean field. So anyway, this is just some things I think should be more in people's minds when they're choosing what method they want to work with. Okay, so conclusions. So I adapted local polynomial fitting for use on the sphere. I introduced a generalized kernel, and I applied it to this problem of mapping sea surface height from oceanographic altimeters. And then sweeping through parameter space with an observing system simulation experiment led to the following insights. Using only a fraction of the data that's available, we're able to produce a product which is rivaling um, uh, the standard product that's out there. And if we did the next phase and used all available data, we would certainly be able to improve on that. Um, Conventional wisdom says that the optimal choice of a smoothing kernel is a parabola, but that the particular choice of kernel doesn't matter that much. And in the ocean mapping problem, that neither of those are true. And this is because your what that inner radius is doing is it's something that's on the scale of the structures you're interested in. So that's why that thing is changing with latitude because the structures you're interested in are changing with latitude. But you still need an outer radius because the role of the outer radius is to grab enough data to make the whole problem numerically stable. So that's why the outer radius is important, but its exact value doesn't matter. Whereas the value of the inner radius is really important because that's the thing that's mapping the typical scales of the structures. Um, Another thing which I briefly mentioned is that there are these class of estimators called plugin estimators where you can try to infer the best choice of parameters um, without knowing the true answer. And those are okay, but they suffer from a they're not really as good as you would like. And the reason is that the best choice of a radius is one that is almost too small. If it were any smaller, it'd be terrible. And the plugin estimators are a little too conservative, and they can't push you up against that almost too small limit. Big picture takeaways, local polynomial fitting with a fit of greater than zeroth order together with variable bandwidth is a great all-purpose mapping solution. And then another thing I'd like to say is that despite lots of theory that's out there, using an observing simulation experiment is a really great step, and it's hard to beat for optimizing performance because oftentimes the way things look on paper and the way they work out in practice are not the same. All right. So that is actually the end, and I have hopefully a publication coming, um, and publications and data set coming, later next year. So thank you.
All right, great. Thank you so much, Jonathan.